exceptions to the octet rule. We're going to look at three different kinds of exceptions. The first one is odd-electron species. If you have a molecule that has an odd number of electrons, you can draw Lewis structures all day long, but there's no way that you can have an octet for everybody. These odd electron things are called free radicals, and they tend to be very reactive. They tend to not be very stable. And that's why free radicals in the environment can be harmful, because they react with things in ways that are not compatible with life. So that's not good. So let's look at one of my favorite molecules. No! Can you bring my lunch to school? No. Actually, I don't say it enough. It's just a fantasy. Because today I brought her lunch to school before she called. Because I went in my van and I'm like, there's her lunch. So I just went. Okay, nitrogen has 5, oxygen has 6. That makes 11, right? So we got 2, 4, 6, 8, 10, 11. Nobody's got an octet. We can do better than that. So let's make a double bond. So we'll go like this. What's wrong with that? Nitrogen has too many electrons, so maybe let's take this guy and put him over here. So now the nitrogen has an octet, 2, 4, 6, 8. The oxygen has 2, 4, 6, 7. Well, close, but no cigar. We could draw that another way. We still need the double bond. What if we gave oxygen the octet and had the lone electron on nitrogen? So what we do is we just write the best Lewis structure that's possible. And then here we've got 2 of them. We're going to decide by looking at formal charges. So what's the formal charge on this nitrogen? -1. It brings 5 to the organization and then leaves with 6 when things get cut in half. So that's -1. And it's not a very big -1. It's just a regular -1. This oxygen has what formal charge? +1. Okay.
When everything adds together, is it always going to be 0?
It's always going to equal the charge on the overall thing. So this is a neutral molecule. It'll add up to 0. So here, what's the formal charge on that oxygen? 0. Oops. We can tell just by looking at it. It's got an octet and it's got 2 bonds. That's what oxygen likes. How about this nitrogen? 0. What? How's that work? Well, it brought 5 in, and when it leaves, it's got 1, 2, 3, 4, 5. 5 minus 5 is 0. Okay. So this tells us that this is the best of those Lewis structures, because it's got the lowest formal charges. Any questions? Another way you can get a violation of the octet rule is incomplete octets. So we already know about hydrogen and helium. They only want a duet. Well, there's a couple of guys down there that are small, beryllium and boron in particular, that tend to be satisfied with 6 electrons. Why? Is because we did this just to get you, right? Just to annoy students. Okay, so let's draw a Lewis structure for boron trifluoride. So put boron in the middle and the fluorines around it. And we've got 3 fluorines at 7 electrons, that's 21. And how many electrons, valence electrons, does boron have? 3. So 21 plus 3 is 24. 2, 4, 6, 8, 8, 10, 12, 14, 16, 18, 20, 22, 24. What seems to be wrong with that? Boron doesn't have an octet. The fluorines do, but boron doesn't. So what we would like to do to make octets, because we really like the octet rule, is we're going to take a lone pair from a fluorine and share it with boron. And now we've got our octet rule. Yay! But what about the formal charges? You have a question? You could take it from anyone, yeah. There would be resonance. There'd be 2 other resonance structures, a total of 3 for this molecule. But let's look at the formal charges. What about this fluorine and this fluorine? Formal charges are 0. That's what fluorine likes to do. It makes one bond. What's the formal charge on this fluorine? Brought 7, leaves with 6. So this is a positive 1 formal charge. And what about the boron? It brought 3 and leaves with 4. It's minus 1. So maybe that isn't so great. So let's unshare those electrons, put them back. These 2 still have 0 formal charges. This one has a 0 formal charge. Brought 7, leaves with 7. The boron brought 3 and leaves with 3. 0 formal charges. This is better, even though it violates the octet rule. The octet rule is something we made up. It's really useful, but beryllium, right next to boron on the periodic table, also tends to have incomplete octets. So it's the little guys. Questions? So we've seen odd electrons, we've seen incomplete octets. We can also have extra big, expanded octets. So the little guys, the really little guys tended to have incomplete octets. The regular sized ones often have octets. And when you get to elements in period 3 and larger, they can have expanded octets, up to even 12 or 14 electrons instead of 8. So we're going to draw three Lewis structures. There's only 2 compounds. We're going to draw 2 Lewis structures. Arsenic pentafluoride and sulfur hexafluoride. So we're going to put the odd guy in the middle, arsenic, and we're going to put the fluorines around it. There's our 4, and we have to put a 5th one in there. So we'll just squeeze him in between the others. 5 fluorines times 7 is 35. How many does arsenic have? 5. So 35 and 5 is 40. 40 dots. Well, 40 electrons. We've got 2, 4, 6, 8, 10 in here already. 12, 14, 16. Oops. 10, 12, 14, 16. 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Yay. It's satisfying, isn't it? Oh, they've all got their octets. It's all nice and symmetrical. So each of these fluorines has an octet. The arsenic has 10 electrons. You say, oh, violation of the octet rule. But what group is arsenic in? It's in group 4. I'm sorry, period 4. It's in period 4. Elements in period 3, 4, 5, 6, 7 can expand their octets. And we're going to see when we get into our next bonding model how that works. For now, we're just going to say you can do that. What about the formal charges? Are you getting to the point where you can see that the formal charges of those fluorines are all 0, right? Fluorine likes 1 bond. They all have 1 bond and an octet. They're good. Arsenic. How many valence electrons does arsenic have? 5. So it brings 5 in. We cut all those bonds in half. How many does it leave with? 5. 0 formal charges. Okay, let's do sulfur hexafluoride.
Arsenic typically likes to make 3 bonds.
Typically, but it can do this also. So this sulfur and 6 fluorines this time. So there's 5 and 6. 6 times 7, 42, plus 6 for the sulfur, 48, right? So I've already got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Kind of looks like pom-poms or flowers or something. All of these fluorines have 0 formal charges, and they have octets. What's the formal charge on the sulfur? 0. It brought 6 electrons to the organization. You cut the bonds in half, it leaves with 6. 0 formal charge. The reason that the period 3 elements and above can expand their octets is that there are d orbitals in the 3rd energy level. And so they're only a little higher in energy than the p, and so they can expand into there and make more bonds. Okay, so let's look at the formal charges on sulfuric acid with and without an expanded octet. So first we'll do without, because we will. So sulfur in the middle, and oxygens out like this, and then the hydrogens are going to be hanging off the oxygens, 2 of them. So valence electrons, 2 times 1 for the hydrogen, and 6 for the sulfur, and 4 times 6 for the oxygen. That's what, 32? I've already got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yay, right? It's all good. It's nice. It meets the octet rule. What about the formal charges? Well, the hydrogens are 0. What about this oxygen? It's happy. 2 bonds. Strictly calculating the formal charge, you think, well, how many did it bring? It brought 6 valence electrons. How many would it leave with? It would leave with 2 lone pairs, and half of each bond, it would leave with 6, 0. So that one's 0, this one's 0. What about this oxygen? -1. And this one would be -1. And what about the sulfur? +2. Because sulfur brought 6 electrons and it would only leave with 4. So that's a +2 formal charge. So this is not ideal. We want to see, well, how could we make them 0? Well, it's not actually resonance yet. Expand the octet. So let's, we're going to keep the arrangements the same, and we're just going to shift around some electrons. So let's leave these guys alone because they were good. 0 formal charges on those. This one had 1 electron too many, and this was short electrons. So how about if we take one of these lone pairs and share it with the oxygen and give this oxygen sulfur a double bond, and then we've got 2 lone pairs left. What's the formal charge on this oxygen now? 0. And how about the sulfur? +1, but it's closer. So we're going to do the same thing with this other oxygen, put a double bond in there. Now this oxygen has 0 formal charge, and the sulfur has a 0 formal charge, and everybody's got 0 formal charges by expanding the octets. So if you can expand an octet for period 3 elements and get the formal charges lower, closer to 0 or 0, then you do that. Period 2 elements never have expanded octets. Carbon, nitrogen, oxygen, fluorine, they can't do this, and so they don't. Any questions? So let's write the Lewis structure for xenon tetrafluoride. Well, put xenon in the middle and put the fluorines around it. Xenon has 8 valence electrons, and each fluorine has 7. So that, I believe, is 36. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I got 4 more electrons. Put them on the xenon. So I'll put a lone pair over here and a lone pair in there. That's it. Looks weird, doesn't it?
Super weird.
We don't want to make double bonds, though, because then we've got even more electrons. We make double bonds when we're short on electrons. That means we need to share more. Here, we're trying to share less, but you can't. So the only thing you can do is put them on the xenon. You can't put them on the fluorines because fluorines are period 3. They cannot expand their octets. And then check the formal charges.
So xenon, even though it's a noble gas, is happy to take on those?
I don't know that I'd say it's happy, but it does form this compound. It requires some encouragement, but it can be done, right?
Kind of like somebody with 6 kids taking on 2 houses.
Yeah. Okay, so here we have our fluorines are all 0 formal charge. What's the formal charge on the xenon?
0.
0. What do you know? It brings 8 valence electrons, and it's got 8 valence electrons if we cut all the bonds in half. So this is okay. Noble gases do form compounds, but they're just very uncommon and you don't find them in nature. Write the Lewis structure for phosphoric acid. If necessary, expand the octet on any appropriate atoms to lower the formal charge. This one is going to look a lot like sulfuric acid. So phosphorus in the middle with 4 oxygens around it, and then the hydrogens go on the oxygen. So we've got 2 electrons from the hydrogens and 5 from the phosphorus.
Is that 3 hydrogen?
Yes. Yeah, 2 times 1.
Thank you. I was just puzzling in my head how the odd electron was going to go away. There's 3 hydrogens. So I can't write a 3 to save my life. There we go. 3 hydrogens. Thank you. 5 electrons for the phosphorus, and we have 4 oxygens, and they're each 6. So I believe that's 32. I would encourage you to use a calculator. It's way over there, but yeah, use a calculator. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 32. 32 electrons. So this looks like it would be great, right? We got the right number of valence electrons, everybody's got octets, we're all good until we look at formal charges. Do the calculations for yourself if you don't see it yet, but oxygen here with 2 bonds and an octet, 0 formal charge, 0 formal charge, 0 formal charge. This oxygen has a formal charge because it only has 1 bond. So it brought 6 electrons, it would leave with 7, that's -1, and the phosphorus would have a +1 formal charge. So then we should expand the octet on which element? The phosphorus. That's the only one that's large enough to do that. So we'll take a pair of electrons from the oxygen and share them with the phosphorus. And now the phosphorus, cutting these bonds in half, would leave with 5. It came with 5. That's a 0 formal charge. And our oxygen now has a 0 formal charge. Any questions?